Welcome to ECE 302. This is lecture 5.7 on examples of a sum of two random variables. I'm Professor Stanley Chan. So if you recall from the last lecture, we talked about how do we sum a pair of random variables. That is, given a random variable x and then given a random variable y, we know their individual PDFs, and we want to find the PDF of a new random variable z, which is defined as x plus y. So last time we introduced the basic principle, which is that the sum of these two random variables, when you look at the PDF will become the convolution of the two PDFs. In today's lecture, we're going to look into some examples. How do we actually compute the PDFs? So this is a recap of the last lecture. We talk about this random variable x, the other random variable y. We say that if you sum them up, that is, you define z as x plus y, the new PDF fz of z will become fx of z convolved with fy of z. This is a very good example that I hope you can remember. It is an example about throwing a dice. So suppose you have a dice which is a fair dice, and you throw the dice once, you'll be able to get a uniform distribution. Now, if you throw the dice twice and then you sum the numbers, then you'll be able to get a triangle distribution. This triangle distribution comes from the fact that you are convolving the PDF of x and then with the PDF of y. Okay. Now, if you convolve it multiple times, that is, you sum more and more random variables. For example, in this case, you're summing 5 random variables. Then the convolution will gradually turn it into something. And as you increase the number of the random variables, we notice that it is converging into a Gaussian. This is called the decentral limit theorem, which we will talk about it later. However, the main thing here is if you sum the two random variables, it is not summing the individual PDFs. The PDFs will be convolved. So what we are going to do today is to really go through some examples of how do we calculate the PDF of z when you have a pair of random variables. Now, I want to stress that the examples that I'm going to show here is not limited to just the sum of two random variables, because the principle that we discussed last time is very generic. It can be applied to other forms of operations. So I want to show you an example of that as well. Okay, so let us start the first example. In this example, I have a pair of random variables, x and y, and they're independent. The form of the PDF is given as follows. You have fx and fy. I'm defining a new random variable z, which is the sum of x and y. I want to find the PDF of z. So let us recall the first principle. How do we calculate this problem? We want to start by looking at fz of z. And then afterwards, we want to look at small fz of z. So the first one is the CDF, and then the second one is the PDF. How do we calculate the PDF from the CDF? It would be take the derivative of your CDF. So this is the way that we are going to use to solve this problem. Okay, so let's start with the CDF. The CDF is the probability that you have x plus y less than z. Now, what is this x plus y? This x plus y, if you are wondering, this is just the definition of the CDF. You have a random variable z. You calculate the probability that z is less than this state, small z. Then you have this CDF. And then now I can replace it by x plus y, because this is how z is defined. And then if you have this probability, then what it means is that instead of integrating the joint distribution of x and y over the entire space, I am going to look at the area specified by this inequality. Okay, so let me finish writing the equation first. So this is the double integration which corresponds to this probability. This probability, of course, is a joint distribution in terms of x and y. And since they are independent, I can just write the joint PDF as a product of the two PDFs. So that comes from the independence. Now the tricky thing, of course, is the limit. Now let's don't worry about these limit. Okay, let's don't worry about this range. Let's just ask a very generic question. What if you have this inequality, right? X plus y less than equals to z. So what would be the upper and lower limit? Now the equation of this x plus y less than z, as we have discussed last time, it will be a straight line here, and then the area that we're integrating will be something on the left hand side, and therefore if you look at the x will go from minus infinity all the way to this line, and this line will be what? This line would be x plus y equals to z, and so you have y equals to x equals to z minus y, so you have z minus y over here, and then now if you want to integrate the y, then the y will go from minus infinity all the way to plus infinity. Okay, so this is really the CDF. The CDF, I haven't really plugged in the range of the x and y's that are non-zero, but never mind. This is a really generic equation that applies to this sum. Okay, it is really about this and then this. They really comes from this sum of two random variables. Now let's still do not worry about the specific form of these two equations. Let's continue our calculation because we want to find the PDF, and we know that the PDF is d and dz of this double integration, and then you have fx of x and then fy of y, dx and dy. And so we know that the inner integration is minus infinity to z minus y. The outer integration is from minus infinity to plus infinity. And so here you have this dz that has to interact with the integration, and we can switch the order between these two. So you have d and dz, and then you have the outer integration, which is from minus infinity to infinity. And so furthermore, we can also pull the y outside this integration, so we have fy of y that is outside the inner integration. Now, when you look at this inner integration, we notice that by the fundamental theorem of calculus, this will give you fx of z minus y. So you plug this equation into the previous case, then you have minus infinity to infinity of fx of z minus y, and then you have fy and y and dy. So this is really the convolution that we talked about last time. Okay, so I hope you have recalled the memory. Okay, so what is the bottom line here? The bottom line here is that let's do not worry about the specific form of x, fx and fy. Let's just write down the equation that correspond to this PDF. And the equation is given by this form. It is the convolution. Okay, so now let's start with this convolution. And what we want to do is to plug in these two specific forms of fx and fy. So what we want to do here is that let's look at this form. If you plug in your fx, what is fx? Fx is given by this equation. You have something, and then you have something else for these two ranges of numbers. So is fy. Now, this fx is non-zero when your x is positive, and whenever you have x that's 0, it becomes 0. And so what kind of value that you can plug in to this equation? Well, of course, your x has to be positive. Okay, your x has to be a positive in order to have some value. If your x is 0, if your x is less than 0, it's a negative number, then when you plug it in, it will just give you 0. So for this convolution to work, we're going to substitute this by, of course, it will be your fx, right? Fx is, according to our definition, is xe minus x. That's given by a problem for x being positive. So if you ever want to plug in this number here, meaning that you want to have fx of z minus y, and just replace this x by this z minus y, then you have z minus y, e minus z minus y. So that's for clear. But don't forget about this range. This range says that you have x bigger than 0. So you have z minus y has to be bigger than 0. Okay, so now if you translate this problem to here, then you will notice that there is a constraint for your y. Your y cannot be arbitrary. Right? So if we do the calculation, we show that y has to be less than or equals to z. Y cannot be an arbitrary number. So that will give you the first constraint. The first constraint is that y is less than z in order for you to use this expression. So what else do we need to care about? Well, the second thing that we need to care about would be this. This is your fy. Fy, I'm going to substitute it with a y and an e minus y, and in this case y is positive. So this is what we need to do for the y. But you notice that this is a constraint as well. So you need to have y bigger than 0 in order for you to plug in the definition of this fy. So what it means is that then we have this pair of constraints. The first constraint is y is less than or equals to z. The second constraint is that y is bigger than 0. So when you combine them together, what do you have? You have y that is between 0 and z. Okay, so now let's go back to this convolution. This is the generic formula that applies to any distribution. Okay, by any distribution, I mean that for any fx, for any fy, I don't need to care about the form. It will be given by this generic equation. If we want to substitute into this equation of my specific form of fx and fy, which is given by these two equations, then I need to worry about the limit of y, because you're integrating with respect to y. And so what is the range of y? The range of y has to be from 0 to z. Okay, so you need to integrate from 0 to z for this integration. So what else? Well, then you don't have to write this form. You just need to plug in this expression here for your fx, and then that expression here for your fy. That will give you this. Okay, so let's see if it makes sense. This form is fx of z minus y, and this guy is fy of y. Okay, and then this is the limit from 0 to z. So if you plug everything in, then you notice that this calculation is not too terrible. Why? So let me erase these equations. Okay, so let's see, why is this calculation not too terrible? You have this e minus y, and then you have e plus y. So these will be gone. And then you have this e to the power minus z, but that has nothing to do with your integration with respect to y. So you can pull it outside the integration. So what you will have left is a quadratic equation of zy minus y squared. And we know how to calculate that. Okay, so you do this calculation and you show that the answer is z to the power 3 divided by 6 times e to the power minus z. And that's true for any z bigger than 0. Now, if your z is less than 0, you can also show that fz is 0. So the bottom line message of this example is really that you need to first go to the basic principle, which is to derive the CDF, to derive the PDF, write down this form. This is the convolution form. Now, of course, if you can memorize this convolution and you recognize that I'm asking you the sum of two random variables, just apply it. Now, there are other problems that are not necessarily the sum of two random variables, which I'm going to show you an example. Then in that case, you need to redo this first principle and then derive that equation. Up to this point, you do not need to plug in the specific equation, which is the specific definition of the fx and fy into that calculation. When you plug in the fx and fy, what you need to do is to look at the range, because you cannot just plug in the equation here, equation that. You also need to care about the upper and lower limit of this integration. Then you look at what are the x and y's and z's that will be allowed. Then you go to the integration and then rewrite the limit. The rest is just calculus. So I hope that this example has given you some idea of how do we actually calculate the PDF of the sum of two random variables. Okay, so now let me go to the second example. In this example, I have again a pair of random variables, x and y, and then they have two specific forms, which I do not need to care about until I do the calculation. And now this thing is a little bit interesting. It is the product of x and y is no longer the sum. And my question is, how do you find a PDF of z? So again, what is the first principle? The first principle is to find the CDF, and then we want to find the PDF. The PDF would be the derivative of your CDF. What is the CDF? Well, the CDF is the probability that x, y is less than z. Okay, so now if you have this xy less than z, then what is this? Well, it would be a double integration of fx, x, fy, y, dx, and dy. That is a double integration for a pair of independent random variables. Now we need to determine the upper and lower limit. That's the generic case. The generic case says that if you have this fx and fy, what is the equation? Well, the equation would be we can write y equals to z over x. Okay, so what is z over x? So if this is y, this is x, it would be a function like this. Okay, so how should I do the integration? Well, I should do the integration. Of course, I cannot. Let's don't worry about the negative part. Okay, so let's only worry about the positive part. So I want to integrate from 0 all the way to this point. This point is x equals to z divided by y. So I should integrate from 0 to z divided by y. That is for my x. And then my y will just go from 0 to infinity. So that would be the range of values for a generic equation, which I do not need to care about the specific definitions of fx and fy. Okay. Now this 0 is, of course, is here because if you only cared about this xy less than z, now of course there's a negative part which I don't want to deal with it. Okay, and so I only want to deal with the positive part, and so I can start with 0. So this is a very generic equation, and we can move forward and calculate the CDF and the PDF. The PDF, of course, it will be integration, and then that is a derivative, and then you have this integration from 0 to z over y of fx of x dx, and then you have fy y dy. Okay, so the outer integration is from 0 to infinity, and then the inner integration it would be from 0 to z over y. So now we ask, what is this guy? This guy is actually not too terrible to calculate, because here you have this z over y, so you can do a chain rule and you can show that this is going to give you 1 over y, and then this is going to give you fx of z over y. So that is done by the fundamental theorem of calculus. This is really the chain rule, so if you do a d over dz of z over y, that will give you 1 over y. Right, so this is how we obtain this 1 over y. The rest is just to plug in this number into your equation. Okay, so now once you have this, then we can conclude that for a generic fx and fy doesn't need to be in this too specific form, then your fz is given by integration from 0 to infinity of 1 over y of fx z over y times fy of y dy. So this is not the same as your convolution, but it is still derived by the first principle. Alright, so how should we do next? So what should we do next is to really plug in the definition of the fx and fy, and then we need to deal with these two integration limits. Okay, so what do I have here? So let's go back to this slide. This slide is just a recap of this calculation of CDF and also the PDF. So let me just make a small change here. It should be going from 0 to infinity. Okay, and you can see that all these equations match with what I have just discussed. So now let us go to the actual calculation. The actual calculation says that I want to plug in my fx of x equals to what do I have here? 2x, for x is between 0 and 1. Okay, so it's 2x for x is between 0 and 1. That is my definition of fx, and then my fy is 1, but y is between 0 and 1. I think it's 1. Okay, so now you can plug in these two equations into the formula, which is here, or if you like, it's the same as here. That is the equation. So now you want to plug in your fx. Then you realize that if I replace this by 2, fx is 2x, right? So x is z over y. I also need to worry that the z over y has to be between 0 and 1. This is how I will replace this fx of x here. Okay, so now if you have this equation with this constraint, then you also need to calculate this constraint by rewriting it as 0. That is z, and that is y. So that will give you the first constraint where y is bigger than z. Now how about we plug in the other equation? The other equation says that this is my fy of y, this is 1, and then y has to be between 0 and 1. So what do I have? Well, since you have y between 0 and 1, then you have the second constraint, which is exactly this. Then you combine the two constraints, then you see that your y has to be between 0 and 1. So that is the overall constraint that is derived from these two, 1 and 2. You combine these two, you have this constraint. So what does it mean? Well, you go back to this equation. So instead of having this integration from 0 to infinity, so integration from 0 to infinity of 1 over y fx z over y and then fy over y dy, you need to put in the limit, which is from z to 1. Okay, and this will become 2 times z over y. This is the definition of the fx. This is your definition of fy. So plug this in, and then you have this integration. So that will go to here. This is the integration from z to 1 of 2z over y, and then there is another 1 over y here, so you have 1 over y squared. You do the calculus, you show that this is 2 times 1 minus z, and that's true for any z bigger than 0. For any z that is less than 0, you can show that the PDF is 0. Okay, so this example shows you how do we calculate the PDF of not just the sum of two random variables, but it shows you how do we calculate the PDF of a pair of random variables when you take the product. The approach is exactly the same. You calculate the generic form, which is the CDF, the PDF, ignoring the specific definitions of your fx and fy. By the time you plug in the specific form of fx and fy, you need to care about the limit. The limit needs to be carefully determined. And then you plug this in, then you will be able to calculate the PDF. The rest is just calculus. So you may wonder how all these exercises can ever be useful in practice. I want to show you one example here, and then I will ask you to read the ebook for additional examples. This example says that I have two random variables, both are Gaussians, and they have different means and different variance. I want to look at the PDF of the sum of x1 and x2. This theorem says that if you sum these two Gaussian random variables, you will indeed get another Gaussian random variable, with the mean being the sum of two means, with the variance being the sum of these two variants. So how do we solve this problem? Well, to solve this problem, we can start with the first principle by calculating the CDF, and then we can calculate the PDF, which is the derivative of your CDF. And since this is just a sum, and we have gone through this exercise already, and we know that it will become a convolution taken in this particular form. So what do? We can plug in the definition of your fx and fy. Now, the integration limit doesn't need to be changed because as a Gaussian has support from -infinity to infinity, so you do not need to worry about the integration limit. The only thing that you need to worry about is to plug in these two equations. Now you have two Gaussians, they are convolving each other. So you ask, what will it become? So the rest is not very interesting, but it's good to know how we actually do the calculation. So let's look at this. You have these two Gaussians, one Gaussian taken in this form, the other Gaussian taken in that form. The first Gaussian is in t, so you have t minus mu1. Mu1 is your first Gaussian's mean divided by sigma. So for simplicity, I'm going to assume that the both sigmas they are the same. Okay, so assume that sigma 1 equals to sigma 2, which is equal to sigma. Of course, at home, you can do a more generic case by having two different sigmas. Okay, so now if you have these two sigmas being the same, then it will be a little bit easier calculation. And then let's go to here. So you have t minus mu1 divided by 2 sigma squared, and then you have z minus t. Why is z minus t? Because the number that you plug in is z minus t. So you have these two. And then now, of course, you have the exponential, and then the other exponential, it will become the exponential of the sum of the two terms. So now you have those two terms here. And then you want to take the integration with respect to t. So you notice that all the complicated things are going with this integration. So we need to just take care of the thing that are living in this exponential. And once we know what it is, then we can do the integration pretty easily. So let's look at the term that we have over here. The thing that we have in this exponential is t minus mu1 squared plus z minus t minus mu2 squared, which is this form. What I want to do is to do a completing square. What I mean is that I expand all the terms. There's a quadratic term, another quadratic term, and then I want to regroup them in a specific way. So I will skip the derivation here, which I believe everyone can follow by yourself. You go all the way to the bottom of this line. Let's recognize what this equation says. This equation says that it will become a constant 2 times a quadratic equation in t, okay, and that is a constant. This doesn't have anything in t, and this doesn't have anything in t. So what I mean is that these two, when you go back to the calculation here, you can really just squeeze them out outside your integration with respect to your t. Take them out, and you just need to integrate this guy. And integrating this guy may not be too terrible because this guy is really a Gaussian distribution of the new mean. And so we have a way to do this calculation. But before we talk about the actual way to calculate this thing, we can sort of do a simplification of this remaining term. This remaining term is minus 2 times the square term plus this term here. You do the completing square and then you rearrange the terms to show that it will become this. All right. So so this can be written as this, and then in the front you have this quadratic equation in t. So what do we have? Well, you have the quadratic equation in t, and then you have this term doesn't have anything to do with the t. So you can move this thing outside by keeping this thing here. So e to the power whatever you have in this equation. And then what remains is the integration. This integration is integrating 1 over root 2 pi sigma square, and then you have this 2 times something something. Okay, that's a quadratic equation in t minus something something. And I really do not need to worry about what that something is because that is just a new Gaussian distribution. The only thing you need to worry about is there's a 2 here. The 2 will cancel out with this 2. And so if you want to keep a 2 there, then your sigma has to be rescaled with 1 over root 2. So what it will turn out that is that this integration will give you 1 over root 2. You can easily verify that because if you have a 2 here, then this integration will give you 1. And so now if you do not have this 2 here, the integration will give you this 1 over square root 2. So if this is 1 over square root 2, then you also have this term here. Then you can show that this entire integration, this entire thing, can be simplified as follows. This is what? This is a Gaussian PDF. The new mean would be mu1 plus mu2 because your dummy variables is your z. So you have mu1 plus mu2 being your new mean. The variance just 2 times the square, 2 times the variance square. And so the variance becomes twice. Okay, so this entire derivation is just calculus plus some completing squares, but it is a very important result. It shows you that if you have a sum of 2 Gaussian random variables, it remains a Gaussian random variable. And then the way to calculate this problem is really to go back to the first principle. When you have the CDF, you calculate the PDF, it goes to with the convolution, and so on. You can show this very important result. What is the implication? Well, if you have many Gaussian random variables, you sum them up, it will remain a Gaussian random variable. So this table here is a summary of many commonly used discrete and continuous random variables. When you have a random variable 1, when you have random variable 2, when you try to sum them up, the sum will have a new PDF, and the PDF will be given by all these equations. And these are very important results because oftentimes you do want to take the sum of 2 random variables. So what is the take-home message? The take-home message, when you try to deal with a sum or products or any other operations of 2 random variables, the principle is to find the CDF, determine the lower and upper limit when you're plugging in the specific form of the PDFs, and then calculate this PDF through this fundamental theorem of calculus. So I hope this lecture has given you some examples of how to calculate the PDF of a function of two random variables. This is an extremely important technique that will be very, very useful when you have engineering problems. Now, this lecture cannot be understood until you do the homework exercises. So I encourage you to do our homework, and please ask questions when you have any questions. This is important because many students they tend to not able to solve problems like these, and they are very important. So I encourage you to ask questions. If you have any trouble, please send me an email or send emails to other instructors. We'll be here to help you on understanding this lecture. All right, so I hope you have enjoyed this lecture, and I will see you next time. Thank you.